Okay, so let's start our class this morning. We have 20 students, I think. Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning to you all. Dan bagi yang berpuasa, selamat berpuasa. Okay, so what we'll do today, I'm going to finish what we discussed 2 days ago on springs. This discussion on spring, and later we are going to talk also about bar, is important because this is where we begin to talk about the fundamentals of modeling and analysis, and whatever type of element, whatever type of structures that you will do, in fact, whatever type of domain that you will do, whether it is structure or fluid or heat transfer, for example, then the procedures remains the same. So we will do the same procedure. So that's why what we discuss on this spring and later on bar is important. Okay, fine. So we are doing recording now, by the way. If you haven't done so, you can do your attendance. The link is on the chat section over there. Fine, so I'm now going to go for presentation mode. Let me do it. Okay, now we are in presentation mode. So let me go to our slide 2 days ago. Fine. Do you see what we have here? Linear spring slide. Can you respond to me on that, please?
Yes.
By the way, can you see my face on the screen as well? You cannot. Are you around? Can you respond to me, please? Okay. I hope everybody is around because nobody is responding to me. Hopefully you are still here. All right, so this is what we have here. Yesterday we talked about this linear spring, and that is our element equation for spring. As we have here, we got two nodes, node 1 and 2 in this element there, and you have also forces and displacements at those two nodes. Please observe that we specify here x-axis positive to the right, and the equation is F equal to KD, you got two forces F, two displacements D, which means that we have 2 degrees of freedom over here. And what you see on the K11, K12, K21, etc., that is the component or the element, the component of element stiffness matrix. That means you need to fill in what is going to be K11, K12, K21, and K22. So that's what you need to do. And we did it yesterday, not yesterday, 2 days ago, by doing this simple approach, which what we call as force and displacement approach. And also some people, they call it stiffness method approach. But in the end of the day, our equation is as what you have there on the bottom right. So that is our element equation. And now we know that the contents that inside the matrix K is going to be the value of the spring stiffness. So if spring stiffness is, for example, 50, K equal to 50 over here, then that means it is going to be 50, minus 50, minus 50, and 50. So that's what we have here. And also, yesterday we talked about a spring structure which consists of two spring as what you have over here. And then we discuss how we arrive at this value. So that's what I'm going to explain this morning. How do we construct the element equation and also structural equation? So for that, then I'm going to go to this Microsoft Paint. So over here, I hope you can see what we have here. If you cannot, just please let me know. I have a finite element model. I have a finite element model of spring system. And in this case, we got two springs. The first spring on the left, it has spring stiffness K1 over here. And on the right, that's the spring stiffness K2. So that means on the spring structure, the number of elements depends on how many springs that we have in the system. Over here, you have two. That means you have two elements, element number 1 and element number 2. So this 1 and 2 is the element number. And don't forget that you need to have the nodes. So we have 1, 2, and 3. We got 3 nodes over here. Node number 1, sorry, node 1, node 2, and node 3. But somehow, the way the model is being given the number for the nodes is 1, 3, 2. It doesn't have to be like this. The best way, to my opinion, is if it is going to be 1, 2, and 3. So that will be easier later on if you want to do your analysis. But in this case here, we have only 1, 3, 2 instead of 1, 2, 3. But anyway, we are going to treat this structure, the model, as 1, 3, 2. Okay, so now let's construct our equation. So I made a mistake. This has to be 1 and 3 over here. All right, so how do we construct the element equation? It is very simple. So we do that by constructing the equation element by element, element by element. So in this case here, we will start with element number one. We will start with element number one. If you look at element number one, okay, the node is node 1 and node 3. Because of that, then the force and displacement matrix is going to be given this number 1 and 3. Also D1 and D3, because those are the nodes for this element. And of course, uh, for the stiffness matrix, element stiffness matrix, then you just simply put the value of the spring stiffness, K1 minus K1 minus K1 and K1. So if K1 is 100, then it is going to be 100. If K1 is 1000, then just put the value of K1 over here. So the same we do for element number 2. For element number 2, the node is 3 and 2. So that's what you do. F3, F2, D3, D2, and for the element stiffness matrix, then it is going to be K2 minus K2 minus K2 and K2, because that is the spring stiffness. So what you will do next is you are going to combine all these F equal to KD, okay? So this is matrix, of course. You will combine this. So you have two equations. The first equation for element number 1 and the second equation for the element number 2. What you need to do, you need to combine this equation into structural equation or system equation. Right, so that's what you do. Okay, I do not draw this properly. It's not that easy using mouse. Okay, right. Anyway, you see what I mean. So on the left here is F equal to KD. You have two equations, 1 and 2, and then you are going to assemble, you are going to combine the equation into F equal to KD system equation. This one here. This is small, this is small, this is capital, this is capital. So before you do this, you need to establish first. You need to establish first what is actually the size of our equation here. And the size of our equation here is determined by the number of nodes. So you have 3 nodes, 1, 2, 3. That means you will have over here, the size is going to be 3. You will have also 3 forces, external forces now, and then this is going to be 3 by 3. Okay, because every node you have 1 degree of freedom. If it is 1 degree of freedom, you got 3 nodes, that means it is going to be 6 degrees of freedom. So over here we have 3 degrees of freedom total. Now what we need to do is we want to add equation 1 and equation 2. But remember that the outcome will be 3 by 3. 3 by 3. So meaning that we need to what we call as expand our matrix from a 2 by 2, this is 2 by 2, into 3 by 3. So actually, the equation that you see on the left is the same as the one that you see on the right. Mathematically, they are the same. The difference is one is given 2 by 2, the other one is given by 3 by 3. But mathematically, you can observe that actually element 1 on the left and equation for element 1 on the right is the same. For example, actually element number 1 doesn't have node 2. So meaning anything to do with f2x is actually going to be 0 actually. Because if you look at this here, if you look at this equation, f2x, so I'm looking now at element number 1, f2x is equal to, so this is what I'm doing now. F2x is 0 multiplied by the 1x plus 0 by the 2x plus 0 by the 3x. Okay, so it will be going to be remains 0. So that's why what you see on the right is the same as what you see on the left. But make sure if you forgot how to do matrix analysis, then please make sure that you look again at what you have learned long time ago on matrix algebra. Fine. So next, we are going to do element number 2. So element number 2 is given here. Okay. And what we will do now is we are going to expand element number 2 from 2 by 2 into 3 by 3. So remember that element number 2 is 3, 2, 3, 2. That is the sequence of the node from 3 to 2. So that's what I do. 3, 2, 3, 2. Okay. And then you're going to expand. Remember that after you expand, then you are going to combine the element. So after you expand, then this is the element number 2. Okay. And you are going to combine the equation of element number 2 after expansion with element number 1. Right. But remember, when you want to add matrix, then they need to be in the same sequence. You see here, 1, 2, 3. So it has to be also 1, 2, 3. Then only then you can combine the equation together. But remember again that from what we did, it is 3, 2. It is 3, 2. Okay. So meaning before you expand, then you need to rearrange. You need to rearrange the sequence from 3, 2 into 2, 3. So we rearrange, then it becomes at what we have at the bottom here. Right? So make sure that you know how to do matrix rearrangement from 2 by 2, sorry, from 3, 2 into 2, 3 as what we have here. Once you have rearranged your matrix, then you can expand from 2 by 2 into 3 by 3. Okay, so what you need to do now is you just add them all together. Combine them all together. Then it will become matrix F equal to KD over here. But this is actually matrix for system, matrix for structure. So that's the way we do our analysis on how you construct your element equation and system or structural equation. Okay, so please make sure you understand this. this is what I'm going to test you on Monday. All right, not test. I'm going to give you the quiz on Monday regarding on how you can do this kind of thing. Okay, is there any comment? Is there any question on this one here? Any question?
No, Prof.
Is there any question from you?
Prof, can I see the rearrange the metric F3X tu dia tukar jadi F2X? The sign doesn't change yang K2 negative K2.
It doesn't change because mathematically it does not change. So specifically for matrix on this type of element, it doesn't change. But if you later on you do your beam, or later on you do your membrane equation, then it will be different. Okay, so meaning that it changes or not, you have to prove it mathematically. You have to prove it mathematically. Instead of you take conclusion, okay, it does not change. It can change depends on your matrix itself actually. And the matrix depends on the element. In this element, it does not change. What you need to do actually as a student, okay, is to try it. You have to try. You have to try with your matrix algebra that you have learned. You have to prove that indeed, actually, this matrix, okay, that matrix, and that matrix, they are the same. So that's what you have to do. And then only when you do it, and then you prove that they are the same. For example, F2x at the top and F2x at the bottom. After you do a matrix analysis and they are the same, then that means they are the same. So that's what you need to do. And then only then you understand whether you understand or not. At the moment, probably most of students, they are only guessing instead of understanding. Okay? All right. Any other question? Fine. So now you have learned how to construct your finite element model, which involve you write your element equation, and then after that you will expand your equation based on the degrees of freedom on your structure. So once you are able to do it, then what you need to do now is you will do your combination. So that's what we arrived yesterday. So yesterday we talked about the same thing. You have element number 1 and element number 2, and we have done our expansion. And then what you need to do is you combine this equation and that equation, and this is actually your F equal to KD. Very simple. Just add what you have on the left and what you have on the right. Internal forces becoming external forces. Displacement remains the same, and the ingredient of your structural stiffness matrix is as what you have over here. Is there any question regarding this? So please take note, K1 plus 0 becoming K1. And then if you look at the one at the bottom right, K1 plus K2 becoming K1 and K2 over here. So that's the way you do it. You need to understand this approach, this method, because when you do your test, probably in, I'm not sure, 3-4 weeks time, probably that depends on when is the test week, okay? You need to be able to do all this kind of thing mathematically. And the only way you can do it is if you practice at home. So now, by doing this, then we understand how we do. Number one, you understand your problem. Number two, you know what element type to select. Number three, you understand meshing. Mathematically, when you do meshing, this is actually what you do. You construct your structural equation, the assembly of the equations. Once you have this, then you will do what we call as introduction of boundary condition. So let's do it. By the way, so this is what you have done just now. Now you have your structural equation, and this is the terms for that equation. And now let's talk about the introduction of boundary condition. Okay, so this is what our structure is. Let me explain this structure and this finite element model. The same as before. Only now I have external force, which is F2 and F3x. So this is given. F2x, for example, 1000. F3x, for example, is going to be 2000, for example. So now what we will do here is we are going to solve the problem, introduce the boundary condition and solve the problem. So what we have here is our structural equation, the same as what we have just now. The same as what we have just now. Okay. So when we introduce the boundary condition, we try to observe which node is not having displacement. The node that will not have displacement is this node over here. Okay, that will not have motion because it is support. It is support. So I can say that node at node number one, okay, in x direction, the displacement is 0, d1x. Displacement node number one in x direction is 0. Remember, if I'm not mistaken, the first quiz that we do, I ask you what you understand about d1, I think d1x or d4y, whatever it is. So d1x, now you know, displacement node number one, x direction is 0. Okay, so what does it mean? It means that, this means that it is 0. You see? That is 0. Why it is 0? Because it is support. It cannot move. D2x and D3x doesn't have to be 0. Those are the variables, the unknowns. In fact, D2x and D3x will be the one that you want to find out. Displacement at node number 2 and displacement at node number 3. Now I ask you, do I know F1x? Please answer. This capital F1x, do I know that?
I think it's not 0.
That's the correct answer. So F1x is not 0. Why it is not 0?
reaction force.
That's also correct. It is reaction force, meaning that you have reaction force there. So it might not be zero. It might not be zero. It will have a value. It will have a value. But at the moment, we do not know. Actually, if I say that f1x will not be zero, that is wrong. f1x can be zero. I repeat again, f1x can be zero. What we cannot say is that it has to be zero because it is a reaction. When you got a reaction, it can be zero. It might not also be zero. Depends after your analysis. What you cannot do is you declare that f1x is zero. I hope you understand these sentences that I speak out just now. Okay, as I speak, these sentences that I mentioned to you just now, that I said to you just now, f1x will have value because it is reaction. But what I cannot say is that it will be zero. It might be not zero. It might be zero. Depends to your analysis. So I hope you see the difference. What I can say for sure is that f1x is a reaction which you need to find. So f1x is variable. f1x is unknown. What about f2x? Do I know the value of f2x? Do I know the value of f2x?
The force
Say again. The answer is do we know the value of f2x external? So do you know or not?
no.
Okay, according to one of the guy, it is no. Can I have the answer from one of the lady? Any lady, please answer my question. Do we know the value of f2x external? Any lady to answer? Or no ladies around here at the moment?
No.
So according to one of the ladies here, the answer is no. No meaning that you do not know the value of external force at node number 2. Okay, we have to be very clear here. When it is given, it is given. It is known. If it is not given, that means it is not known. So if you see in the problem here, we have, look at this here. At node number, you got f2x. That means it is given. Look at node number 3 here. f3x, that means it is given. Okay, so the value of external force at node number 2 is f2x, given. The value is f2x. What you need to understand now is that when you do engineering or modeling, okay, sometimes we just put a term f2x. The value can be anything, but that means it is given. Okay, so I hope it is clear. If you don't understand that, you will be in trouble when you are trying to solve this finite element analysis. So the conclusion, f1x I do not know. It is a reaction. F2x I know because it is given. F3x I know because it is given. Fine. Now let's do mathematics now. What you see on the left here is the same as here. So if you do your matrix analysis, then you will find out that F1x is K1 multiplied by 0 plus K2, plus 0 multiplied by D2x and minus K1 multiplied by D3x. That's what you see over here. So from here, if you understand, then that's good. If you don't understand, then that means you need to read again your matrix. And the second equation relates with F2x. The third equation relates with F3x. Minus K1 multiplied by 0, of course 0, minus K2 D2x, and K1 plus K2 multiplied by D3x. So over here, I forgot, but you should have D3x over there. D3x. Okay, it's not good. Anyway, you know that it is D3x. Okay, so meaning now that what you see on the left here, matrix, is the same as what you have here on the right. These are algebra analysis for matrix based on the matrix on the left. So that's the reason why when you are at high school, I think when you are at level 4, probably you learn matrix. That's the reason, because you have to use it in this course. Now, let's do some observation. Please answer my question. Do you know these 3x or not? Please answer my question. Do you know these 3x or not?
No.
Can I have the answer, please? Do we know these 3x or not?
No.
That's correct answer. Do we know D2x or not?
No.
I think I have to stop now. I think everybody is tired. Okay, so I will stop this course, have 15 minutes break, and hopefully after 15 minutes break, when you come back, then you are okay. And you can answer my question. All right, so I'm going to stop now, and we have 15 minutes break. And then after that, hopefully, when we come back, the discussion is going to be more meaningful. Okay, so 15 minutes break, and we will start again at 5 minutes past 9. Okay, so see you again. Okay, so let's continue with our class today. So let me go back to that discussion that we left just now. Okay, so this is our problem here, a two-spring system, and you have this structure. This consists of two springs. We understand that this is our structural equations or system equation. And we understand as well that the displacement at node number 1 in x direction, it is 0 because it is a support. So because of that, I can put here for d1x as 0. And then mathematically, we can do matrix algebra, matrix multiplication, and then that's what you have here on the right. This equation, if we observe f1x, I do not know because it is support. f2x and f3x, these are given. Look at this arrow here, meaning we can provide a value over there, it is given. Now, d2x, which is over here, and d3x, which is over here, we don't know. We do not know because those are variables. Okay? So we have three equations over here. We have three equations, equation 1, equation 2, and equation 3, but they have only two, but we cannot solve this. The reason is because mathematically, the matrix is cannot be solved, if I may say so. Let's say we look at the first equation. K1, I know the value. If you buy the spring, then of course you know the value. If you decide I want to make use a spring, then make sure you know the value. So K1 you must know, definitely. D3x, you do not know. That is unknown. F1x, you do not know. It is support. You need to find out. So meaning this first equation, okay, this first equation is meaningless, if I may say so. That means you cannot solve it because you know that there is D3x on the left that you do not know. There is F1x on the right that you do not know. That means you cannot solve this equation. So you remain only with these two equations. So if we look at the equation number 2 and 3, okay, then we can solve it. The reason is because f2x and f3x, you know. d2x, d3x, unknown, of course. Don't forget that we have actually d3x over there. So I forgot to put it there, but there is d3x over here based on this matrix. So you can solve this. You are able to solve this equation. This is two equations with two unknowns. The unknowns are d2x and d3x. Okay, displacement at node number 2 and node number 3. From what you have learned in numerical analysis, this is what we call as simultaneous linear equations. Two equations with two unknowns, meaning that you can solve this using what we have learned, Gauss-Jordan, Gauss-Seidel, or Koleski, or Gauss, whatever. Okay, so you can solve it. And actually, if you look at this equation, you can write this equation as a matrix. Okay, so that equation that you see over there, you can write it in matrix. So this matrix here at the bottom here, okay, mathematically is the same to these equations. All right, and this matrix can be solved. This matrix cannot be solved, but after you introduce the boundary condition, after you introduce the boundary condition, okay, then you end up with this two equation, which is actually, from matrix point of view, is this equation. Okay, so with that, then you can solve this matrix. I think somebody tried to guess in. Fine. So as I wrote here, D2x and D3x can be found, right? If you can found D3x and D2x, D2x and D3x, okay, then you will be able to find F1x this year. Okay, if you know D2x and D3x from this equation, or from this equation, after you solve it, then you can find the value of F1x, which is the support over here, because you know the value of D2x and D3x. The value of D1x is, of course, 0 because it is support. And also, if you cross-check, then you can also check F2x, F3x, and if you do it correctly, then the value of F2x, F3x that you find from here is going to be the same as what we have over here. Okay, now I would like you to do observation. If you compare these two metrics, this and this one, so actually I can get this matrix by understanding that D1x is 0. Okay, D1x is 0. So D1x, that means I'm talking number 1. What you could do is, I know that D1x 0, that means row 1 and column 1, I can delete. And if I delete row 1 and row and column number 1, because this relate to displacement 1x equal to 0, then you end up with this matrix. So after I delete, after I cut out row 1 and column 1, then you see here that we have this equation, F2x and F3x, and they are the same with this equation. Okay, so I hope you understand this explanation. Okay, because this explanation is important for you to be able to do calculation analysis on finite element. As you can see now, what you have done so far, you know the structure, you build the finite element model, and then for every equation, you build the element equation for element number 1 and element number 2. And then after that, you expand as each equation. After you expand each equation, then you combine the two equations, then you will obtain this structural equation. And then you introduce the boundary condition, displacement equal to 0 at node number 1, then you end up with this equation. So this is equation, structural equation, after you introduce the boundary condition. And then after that, you can solve D2x and D3x. By doing that, then you know the value of D1x, which is 0, D2x, and D3x. If you know all this displacement, you can find the support. And also, you can find the internal forces of each element, because internal forces of each element, you find it from this equation. Okay, so with that, then I finish our discussion, our lectures on spring structure. And as I mentioned, this is becoming the basis of our analysis. Is there anything that you don't understand you want to ask?
So Prof, lastly, the value of F1S will be in equation form, right? I mean, from that question.
Can you repeat the question, please? I'm not so clear with the question.
Hello, Prof. Again, lastly, the value that we want to look for is the reaction as at F1S, right? F1X, yes.
Not only that one. What you want to find out actually is number one, displacement at every node. And you find displacements at every node by solving this equation at the bottom. This equation is, of course, the same with this equation here. So how you solve it? Using Gauss elimination, for example, or whatever method that you can do. By doing that, you can solve D2X and D3X. Why you can solve D2X and D3X? Because you know the value of F2X and F3X. It is given. You see here, it is given. Meaning, D2X, D3X can be found. Once you know D2X, D3X, okay, you got your displacements. That's number one. Then you can find the support reaction by doing this equation. Okay, so I'm going to delete all this. So by doing this equation, which is your structural equation, and of course B1x is 0, you can find F1x. Because F1x is going to be K1 multiplied by 0 plus 0 multiplied by D2x, of course you know D2x, minus K1 multiplied by D3x. And D2x, D3x, you can find it from here. So now you find the support reaction. Number one, you get your displacement. Number two, you got your support reaction. Number three, what you need to find is internal forces at every element. So meaning now you need to use equation for element number one to find the internal force of element number one. Excuse me. And the same for the element number two. So what are those equations? That is the equation that you have learned. So for example, if let's say this is equation number one, for element number one, then you want to find out what is internal force at node number one, internal force at node number two. How to do it? By doing this calculation. K multiplied by D1x minus K multiplied by D2x. That is F1x. F2x minus K multiplied by D1x plus K multiplied by D2x. That is going to be F2x. So by doing that, then you know F1x and you know F2x. If F1x is positive, it will go to the right. If F1x, the result is negative, it will go to the left. If F2x is positive, it will go to the right. If F2 is negative, it will go to the left. Then by doing that, then you know the internal force of element number one. And that will be the force that element number one is going to feel. I repeat again, that will be the force that element number one is going to feel based on what you find F1x and F2x. You will also find out whether element number one is going to be in tension or in compression. Okay, whether element number one in tension or in compression, that depends on the value and the direction of F1x, F2x. I repeat again, F1x, F2x, those are internal forces, not external forces. Okay, why you can find it? Of course, you can find this because now you have obtained D1x and D2x. So number one, you find your nodal displacement. And then after that, you can find your reactions. And then after that, you can find the internal force, what the spring feels. So I hope I answer that question. Any other question?
Prof.
Yep.
So basically, the value for the D1x and D2x for the element equation and also the structure equation is the same value, isn't it?
You are correct. So
Okay.
displacement matrix for element and also for system or structure, they are the same. The value, they are the same. But the force in element equation, those are internal. The force on structural equation, those are external or applied force. So those are different. Any other question? Okay, so I think with that, then we can close the spring. And now we will go to a structure that is probably more meaningful to you. More meaningful meaning that it is, I'm not saying that spring structure is not realistic, but probably bar structure is more common, okay? More common. So now let's go to let's talk about the theory of bar structures. I'm not going to give example for this spring here. So I'm going to go straight to bar structure. Hold on, let me check what do I have here. Okay, this is spring. This is spring. Now let's go to bar. Okay, let me check. Do I have that one here, spring and bar? I hope you still remember. We talked about this on Monday. So this is bar structure. And as I mentioned, in bar structure, every element, the axis of every element, let's say we are talking about this on the right, the axis of the element number 1, number 2, and number 3, they are vertical and in the same axis. And also you can observe that at every load, each load, 40, 14, 25, they are also in the same axis. So what does it mean? It means that everything on this bar structure must be in the same axis. No more, no less. And then we call this axial structure because the structure and the load, they are in the same axis. And if you observe this structure on the left and also the structure at the bottom here, again the same. The loading, this 150, is in the same axis to each component. To each component. I shouldn't say element, I should say each component. So for what you have here, this is not finite element model. This is a structure. So I'm not going to call it finite element. So the component on the left, the axis you see is in the same axis to the load. The component on the right, the blue color, is the same. And if I say the structure itself, the axis of the structure is the same as the axis of the element, the component. And the same also to the load. That means it is axial structure. If you see this kind of problem, then the element that you are going to use is going to be bar element. Right? Now that's what we want to learn. Element equation of bar. So now let's go to bar. Over here. Let's look. So now let's look at this bar element. Number 1, it looks like this. When we talk about bar, then we don't talk about spring stiffness. When we talk about bar, hold on. Okay, probably I do it there. Okay, it's okay. You have the length. I call it L. Okay, you got the length of the bar. I call it L. You know the cross-sectional area of the bar. Cross-sectional area. I call it A. You know the material. You know the material. That means I know the modulus of elasticity. I call it E. So when we talk about bar, we don't talk about spring stiffness K. No, we talk about A, E, and L. Area, modulus Young, and length. Okay, so now we are talking proper structure. Now, when we talk about bar, we have two nodes as well. Node number 1 on the left. Node number 2 is going to be on the right at the end of your bar. And then, of course, you are going to have your X direction. X direction, axis. What is U? U actually is displacement. You have learned from strength of material. Displacement at X, I call it U. Displacement at Y, I call it V. And displacement at Z direction, I call it W. So meaning displacement X direction, I call it U. Anyway, from here also, meaning that whatever we do is on the X direction. At node number 1, well, you have this, force and displacement. At node number 2, you have this, force and displacement. Then, of course, it is going to be in this equation. Your F equal to KD is going to be F1x, F2x, D1x, D2x. So meaning now, you need to find out what is actually the ingredients of matrix K. K11, K12, K21, K22. And of course, from here, I hope you can observe, you agree with me, that value of the ingredients of K here must be based on this. All right? So that is the introduction. Another thing that you can observe, it looks so similar to spring. It is the same axial, X. You got two nodes, 1 and 2. And the force, displacement components, they are the same. Then, this is a very similar in behavior to spring. The difference is only on the ingredients of your K. On spring, look, they are similar. They are similar. K11, K12, K21, K22, we solve it, and it is this, spring stiffness. In our bar, that's what we are going to do. We want to find out what is actually K11, K12, K21, K22. And for that, then we go here. So again, if you look at this here, this is again similar to what we did with the spring. Physically, what happened here is that if you have a bar, you apply the force left and right, the same magnitude of force, of course, because it is structure, action, reaction. Okay, you got all the ingredients over here. You do tensile force, then you have extension delta, right? I hope by now you know where we want to go. Now, let's go to the next page. Okay, so let's look at this equation. T, okay, is the force. So must be T, force equal to the cross-sectional area of the bar multiplied by the stress. Due to the tensile force, then of course there will be stress in the bar. And that is the relation. Force equal to area multiplied by the stress. Definitely. That's what have you learned. That's what you have learned. Why I've got X? Because it is in the X direction. And from material, you understand that the stress is equal to modulus of elasticity E multiplied by the strain. Okay, so epsilon is the strain. This is Hooke's law, by the way. Hooke's law, which says that stress equal to E multiplied by epsilon. E multiplied by epsilon. Okay, so these two equations will become the basis for us to derive our element equation for the bar. There is nothing for me to explain here because this is something that you need to understand. You are a final year student, you should know this kind of formula. Force equal to area multiplied by the stress. Stress equal to modulus of elasticity multiplied by the strain. And you have learned from material science that strain, okay, strain is actually elongation divided by initial length. So strain is actually this elongation here divided by initial length. That is what we call as strain physically. Now, we learn from the spring that elongation delta must be equal to d2x minus d1x. Okay, so this delta here, this delta must be equal to d2x minus d1x mathematically. You have to agree with me on that. Then that's what we write here. Epsilon is equal to d2x minus d1x divided by L. So what we have here, I know my strain. And that strain, you can put it there. Okay? So, meaning stress equal to E multiplied by what we have here. Okay? And you substitute that stress sigma over here. Then you have this equation. E equal to A multiplied by E multiplied by the strain. Then that is your equation.
Prof.
Yep.
You forgot to record.
Okay. Hold on. It's a bit late now, but anyway, I tried to record. It's becoming not organized. Let me go here. Actually, I'm a bit surprised that I can do recording because yesterday I also got a class and I couldn't do the recording. What do we have here? Right. By the way, if you have anything to say to me, I think better you talk to me directly because when I'm teaching, I don't look at the chat. So anything that you want to say, better you shout out to me rather than you write on the chat section. When I teach, I cannot see the chat section. You could, but I cannot. Okay, where am I now? Okay, now we do the recording again. Somehow I close the record probably during the break. Okay, where am I now? I have to come back here. Okay, so this is our equation for bar. So again, the same as to what we have done on the spring. So this F1x equal to minus T, F2x equal to T. That is because this observation, this F2x must be that force. And this F1x must be that force. Only now that F2x is positive T, F1x is negative T. Okay? So because of that, then that's what we have here. F2x positive T, F1x negative T. But we know, now let's look at F2x. F2x equal to T, and T is this. So that's what we have here. F2x equal to t. F1x equal to minus t. What you need to do is simply just you exchange d1x and d2x. So this is positive t. This is negative t. Observe it is d2 minus d1. It is d1 minus d2. Again, we do the same as what we have done on our spring. This is two equations. All right. And then I write that equation in matrix. So that is our F equal to KD. So F1x and F2x, what we have over here, is the same as what we have over here. So for anybody who understands this, that's nice. For you that you got confused with this equation, please look again at your matrix analysis, because you need matrix analysis to answer this type of problem. So what's the conclusion? The conclusion is very simple. Now you know your element equation for bar element. So that is your equation. Now let's compare this equation with spring. Where is our spring? That is spring. See? F1, F2, D1, D2, all are in X. And then the content, the ingredient of this matrix is K minus K minus KK. Over here, I can read this AE over L minus AE over L minus AE over L, AE over L. So now you can say that what we have as K in spring, over here it is becoming AE over L. So meaning, if you know and you can do spring, that means you understand and you can do bar. Is there any comment from this? Any question regarding what we discussed just now?
No, no question.
Okay, any question? So from what you have here, then now actually you can do bar structural analysis, because you have seen the way we treat, the way we do spring. That means you know spring, you know bar. The difference is what? The difference is only on that equation that you have over there. AE over L minus AE over L minus AE over L and AE over L. That is the difference. Okay, right. So now I'm going to quickly, because we don't have much time, and this is a fasting month, so everybody, include me, probably a bit slow. I feel slow actually. This is quite normal, right? Some people might be becoming very bright when they are doing their fasting. Well, I'm probably uh, a bit slow when I'm doing fasting, because you need oxygen, glucose, I suppose, on the brain, which is now not sufficient, I suppose. Okay, anyway, no complaint about that, of course. We do fasting and do working. That means we got the pahala, you know. Or probably we call it jihad, probably because you are studying, right? Okay, what now? All right, now let's look at this. Let's look at this. So that is a finite element model, actually. Finite element model, pardon me, it is not in SI, it is in imperial unit. It is in the imperial unit. So let me draw. Actually, the structure look like that. Sorry, bad drawing. Okay, and then you get the support. It's also not good the way I draw it. All right. So that is our structure. And then the loading is somewhere over here. There. And, sorry. Am I going to do this? There. And the value is given 10,000 and 10,000. Okay, so that is our structure. If I give you the question, if I give you the test, for example, right, or quiz, as now you are aware, I give you the structure. The first job you do is you build the finite element model. Okay, but of course, you know the value of your loadings, you know the dimensions, you know everything, you know the material. Okay, you know everything. So meaning now that based on that structure, you build the finite element model. So why the model looks like at the bottom there? Very simple. So now let me change the color. This is very slow. So you see I'm doing this in a very primitive way. I'm working with a mouse. You see the mouse over here? That's why all the drawing is not tidy. Number one, you need to develop your finite element model. What is the rule? If you have the load, you got the node. Number one. Sorry. You get the node over. Oh, wow. How am I going to do this? So you have the node of over here. Okay, that's the node. You see the black color there. You have the load, you have the force, you have the node. Okay, so I'm drawing the. Good Lord, this is so bad. Another node. Pardon me, very ugly. When you have support, you got the node. So I'm drawing the node over here, like that. If I have the support, I have the node. So another node over here. Okay. Do I need more nodes? No. Because, well, based on our principle, you have all the nodes that you need. When you are at the end of your structure, you must have a node, but you already have the node over here. So no need. Now we do the numbering. Node number one, node number two, number three, and number four. Don't forget that is your x-axis. What about element? Of course, you will have element number one, element number two, element number three. Nice. So you see here, I have my finite element model. And that is exactly what you have here. That is your finite element model. So again, whatever you do, that is the first thing that you need to construct. That is finite element model. And the material is given over here, cross-sectional area and modulus of elasticity. It is PSI, pounds per square inch, because it is in imperial unit. You know the length of everything here. You know the forces. Now answer my question. You have to answer. What is the value of F2X? Give me the correct answer. F2X. Don't worry if the answer is wrong. I accept wrong answer. Okay, ladies, gentlemen, what is the value of F2X?
Negative 10,000.
Negative 10,000. It is correct answer. Negative 10,000 pounds. So from here, you know that F3X is going to be 10,000 pounds positive. Right. As you see here, this is very important. That's why you need to understand this first before you do anything else. What about D3X? Anybody want to answer D3X? Can you answer me? What is D3X? What you know about D3X?
Variable or not equal to 0.
D3X is unknown. It is variable. That means you need to find out. When you find out later, most probably it doesn't look like 0, but it can be 0. Depends on the setting of the load, everything. Okay? So in this case here, it is not 0. The answer is not going to be 0. But on other situation, the variable, the unknown, after you do the calculation, you can find out that actually it is 0. But what you cannot say in this case is that D3X must be 0. What you will say is D3X is unknown, the one that you want to find out. However, if I'm talking about D4X, then you can say with confidence, with distinction, that D4X is 0. Nobody can deny that because D4X is support. If it is support, then that will be 0. So I hope you see that that concept. Okay? What about F4X? Anybody want to answer? How am I going to do this? Can you answer what is F4X? Sorry, it's so ugly. The ladies are very quiet in this class. You lady, you want to answer that? Anybody? Our student, ladies, you want to answer that? What do you know about F4X?
Reaction force that can be 0.
Okay, that is a very careful answer. F4X is of course reaction. Okay, I agree with that. It is unknown. Okay, and F4X, you cannot declare that F4X is 0. What you can declare, F4X is a reaction force which you want to find out. It can be 0. It might not be 0. It can be 0. It might not be 0. But you have to calculate first. What you know at the moment is that F4X is actually variable, unknown. So in this case here, F1X, you do not know. You have to find out. F2X minus 10,000. F3X 10,000. F4X, you do not know. You have to find out. What about displacement? D1X, 0 definitely. D2X, it is variable, you want to find out. D3X, it is variable, you want to find out. D4X, it is actually very clear, it is 0 because it is support. Okay, so how are you going to solve this problem? Very simple. Pressure wise, equation 1, element 1, equation 2, element 2, equation 3, element 3. Find those out. How? Of course, you know the equation. And then you do the expansion, because if you look at this problem, element equation is 2 by 2. So now I'm asking you, the structural equation, I have 4 nodes now, 1, 2, 3, 4. What is the size of the structural equation? Can you answer that?
Four by 4.
That is correct answer. Element, now let me explain this to you. The element the bar element, where is that of yeah, okay, the bar element consists of two nodes. Every node single degree of freedom in x direction only. That means for this bar element consists of two nodes, you got 2 by 2 over here. Now let's talk about this. Let's start over here. You look at this here. 1, 2, 3, 4. You got 4 nodes on your structure. 4 nodes on your structure before boundary condition. Okay, you got 4 nodes on your structure. So the size of the structure is going to be 4 by 4. Why 4 by 4? Because you got 4 nodes, every node single degree of freedom in x only, displacement in x only. D1x, D2x, D3x, D4x. That's why you got 4 by 4 size of structure. Okay, 4 by 4. And then after that, 4 by 4, the size of K, the big K, 4 by 4. What does it mean? It means that you need to expand your element equation from 2 by 2, into 4 by 4. You do it first. How to expand? We discussed it just now. You write your element equation, and then you expand your element equation from 2 by 2 into 4 by 4. Okay? And then after that, you combine all those equations. You have 4 equations. You combine them all together after expansion, and then you are going to have your capital K. 4 by 4. Okay? So that is before you introduce the boundary condition. After you introduce that boundary condition, it is going to become 2 by 2. Why 2 by 2? Because if you look at our model, D1x, D4x, they are 0. Initially, before boundary condition, you have D1, D2, D3, D4 in x direction. After you introduce boundary condition, you know D1 and D4, they are 0. That means remains only D2 and D3. That's the reason why your equation is becoming 2 by 2. So I hope you understand that explanation. So by doing that, then you construct your finite element model, introduce boundary condition, and then after that, you are going to solve using Gauss elimination D2x and D3x. Once you got D2 and D3, you can find what is going to be F1x and F4x. And then you can find the element equation for element number 1, element number 2, and element number 3. Then you know the internal forces. We cannot do that now. Time is up, and we are tired. That includes me. Yeah, so we will talk again about this on Monday. Before we talk about this, I'm going to check your understanding on what we have discussed just now by doing quiz number 3. Okay, as usual, we start at 8:15. And your quiz number 2, I will return to you as usual at weekend, during the weekend, Saturday or Sunday. Okay, so then you can learn from the quiz, and also you learn from what we have over here. All right, so I think that's it. You can read, you can go to the recording and listen to what I explained. By the way, before I close this, is there any question from you at all? Question? Okay, so that's it. So what we are going to do, please do your study. Monday, we are going to talk about this again after we do our quiz. And we finish the bar, and hopefully we can cover trust on Monday. And next Wednesday, we will do fully on the lab. Next Wednesday, we are going to do fully on the lab. We are going to do trust analysis using using ANSYS. I almost say using MATLAB. Task analysis using ANSYS. That's going to be for Wednesday next week. Monday next week, we are going to talk again about the bar, and we are going to cover the truss as well. Okay, so I think that's for today. I'm going to finish now. Thank you very much. So yeah, hopefully we meet again, inshallah, on Monday. So that's it. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and good morning. Selamat berpuasa. Take care and keep healthy. Thank you.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof. And selamat berpuasa.